Uh, Hello. This is this will be our first lecture for CS33. So, for our first module for CS33, we will be focusing on binary trees. So, um, I think as explained during the introduction to this course, CS33 will focus more on um, nonlinear data structures as compared to the data structures that we discussed in CS32, where we focus on linear data structures. So now we focus on nonlinear data structures. And the first topic that we will be covering will be binary trees. Um, for the succeeding part of this lecture, please expect that I will be dividing this lecture into smaller uh, pieces so that it will be easier for you to watch the videos, and so that you won't need to spend a full 1 or 2 hours just watching the video. So I will try to keep the division by 10 to 15 minutes. So we will start with binary trees, and I believe that binary trees is something that you already discussed in CS30 or CS31. And one thing that I want you to see as you listen to these lectures, and as you look at the supplementary materials that we have shared to you, is that I want you to see the difference in the approach that we will be taking as compared to when you were studying trees in CS30 or CS31. Because for CS33, we will be looking at trees as a data structure, number one, and we will be looking on the algorithms that we can use and that utilizes the binary tree data structure. Okay, so moving along, so a binary tree is a finite set of nodes which is either empty um, or it consists of a root and two other disjoint binary trees on the left and the right subtree of the root. So essentially, when we say a binary tree, it has a number one, a finite set of nodes. So we will not have a binary tree that will have an infinite set of nodes, which is either empty. So we can actually have an empty binary tree, or it can be consist of a root and two disjoint binary trees on the left and the right subtree. So I want to emphasize that the definition itself is recursive. Why? Because we are defining a binary tree, and in the definition of the binary tree, we are also using the same term, the term binary tree also. So essentially, we have a root, and we have two binary trees. We have two sub trees, which is the left and the right subtrees. So these are examples of binary trees. Obviously, one thing that we can easily notice is that for each node or for each vertex, there can be no subtree, there can be one subtree, or there can be two subtrees. From the term binary tree itself, or from the word binary itself, we can see that we can have at most two possible subtrees. It's a binary, so the root word bi is used. So we will now look at some key terminologies um, on the that we will be using as we move along this lecture. So I think one important terminology that we should always remember is the term root. So the root is the node that is at the top of our binary tree, and then we also have that term level. So the level of a node or a vertex is is distance from the root. So the root is obviously at level 0. Node L and E are at level 1 because they are one level away from the root. node G, I, H, S are at level 2 because they are 2 levels away. And obviously, node O, R, and M are at level 3 because they are 3 levels away. So some more terms are height. So essentially, the height is the highest level in the binary tree. So we have here a binary tree of height 3. We have the root, as I explained earlier. The leaves are the nodes that have no children. So when we say node or vertex, they are basically the element of our binary tree. When we say parent node, so we always refer to a parent node relative to a particular node. So for example, for node L, the parent node of node L is A. The parent node of node I is L. Those, that thing. And at the same time, we have the term child, which is basically the opposite of the term parent. So the child node or the children node of node L are G and I. M is a child node of H, and so on. So the Hendon test so their definitions are pretty obvious. So the descendant of A are all these vertices or all these nodes. The descendant of H is M. Ancestor is just basically the opposite of the term descendant. We also have the son. So it's just another term for child. Father is just another term for parent. Brothers, these are vertices or nodes that have the same parent. Okay. Um, Maybe just as a disclaimer, as you can see, we have masculine terminologies. We are using son, father, brother. Um, this has nothing to do with the gender or or being being more masculine in our terms. The reason why the term son, father, brother, or the reason why we are using the masculine terminologies, why we are using masculine terminologies, is basically because it will be harder for us to spell daughter because it's a lot longer and it's not that easy to use, especially if we are typing, if we are coding. So it's something that we don't want to use because that can be a source of misspelling. And of course, son is a lot easier to spell than daughter. So that's the only reason why we are using the masculine terms here. I think some interesting questions that we can look at before we move to our next topic is number one, what is the maximum number of nodes at level I? Obviously, since for each vertex, for each level, I mean, you can have one node and have each child. So at level 0, obviously, we have only one. At level 2, we have only two because the node can have only two children. At level 3, we can have four because the left node can have two other children and the right node can have two other children. So obviously, at level I, the the number of the maximum number of nodes is 2 to the I minus 1. So what is the maximum number of nodes that can be found in a tree of height h? So basically we will just add 2 to the 0 plus 2 plus 2 plus 2 squared plus 2 cubed up to 2 to the h. And knowing that because each term represents the maximum number of nodes at one level. So if we will sum them up, so the maximum number of nodes that we can have in a binary tree of height h can be 4 raised to h minus 1. We can easily prove that using induction. If n nodes will be placed in the tree, so what is the maximum minimum height of that tree? So the maximum height is obviously n because we can have a tree that will have one child at each level, and the minimum height, and you can verify this later on, will be log of n base O, the floor of that. Okay, so we will round it down. Okay, so um, in the next video, we will be looking at different classes of binary trees, different kinds of binary trees, and we will be looking at how um, we can actually how these type of binary trees are being used in certain applications.